So now that we've got this approximate model, we want to go through and develop an analytical technique that we actually can solve for the temperature profile 1D transient. What we are going to find is that this problem becomes kind of difficult. So what I'm going to do is just go through and derive the differential equation. We'll get to that point. You'll see what it looks like, and then we'll basically have to leave it there and then move to numerical techniques. But let's just go through the control volume analysis because I think it's really useful to just understand what's happening. And then we'll leave it at the ODE for this time. So the energy balance that we have some domain and we have a control volume. So in the control volume, we have conduction. That's Q dot at some position x, right, where this is the x coordinate. That heat transfer is occurring, let's say, to the right. In this control volume that I'm drawing, this is a differential control volume. This differential control volume has to apply for the entire domain. So we do have heat leaving here, right? I didn't draw this control volume so that it sort of arbitrarily included all the temperature profile. Like this has to apply everywhere. So we do have Q dot at x plus dx occurring. The width of this, let's call dx, as we always do. And then we're going to note that in here, there's internal energy change. So first we're going to do the control volume, right? We do the do CV analysis. And then second, let's do the energy balance. So the energy balance is again in plus generated is equal to out plus stored. We don't have any generated in this case, but we do have in, out, and stored. Let's collect the terms then. Q dot x is in, out is Q dot x plus dx, and stored is du dt. Let me be a little careful here. So I've gotten a little sloppy already. This equation that I'm going to write is going to involve a change in temperature and a change in time. So I've written it as du dt. In fact, that's wrong. It is the partial u with respect to time. And it should be changed over here in the energy balance. This is the partial of u with respect to time. So we're only looking at the change in internal energy with respect to time. That means that when I write out my Fourier's law, I also need to write that in terms of partials, not in terms of the ordinary differential. So let's expand out the term. We get Q dot x is equal to Q dot x plus partial Q dot x partial x times the differential width, which is just dx. Right, that's not a partial. Plus partial u with respect to time. Q dot x's cancel. And we can simplify down to the equation partial Q dot x partial x dx equals, let's see, du dt. So let's actually write an equation for internal energy. So that's going to be minus because we're bringing the Q dot x over to the other side, minus rho c volume, which is AC, times dx, right? Volume of that control volume, AC times dx, times now the partial with respect to, partial with respect to time. That was right. Things to note here, right? dx has to cancel out, as it always does. And then we're left with the remaining equation, which is this partial differential equation in terms of Q dot. Let's introduce Fourier's law for this Q dot here. So partial with respect to x of minus k AC partial t partial x is equal to minus rho c AC partial t with respect to time. Now you'll notice AC also cancels out. In this case, it's a plane wall, right? The constant cross-sectional area. And then finally, we can bring minus k over to the right-hand side. Right? So this is minus k, that cancels. Right? This is just alpha, 1 over alpha. And so our final differential equation is the following. It is partial squared temperature with respect to x is equal to 1 over alpha partial T with respect to time. So this is our governing a partial differential equation, right? P for partial in temperature. This differential equation involves both the variable, independent variable x and the independent variable time. The solution for this type of equation, there's different ways to do it. You could use Laplace transforms. In some cases, you can use separation of variables. Those techniques that you could use are actually beyond what we're going to talk about. What we're going to do in this class now is just take numerical techniques and throw them at this type of problem and solve them numerically. So while we're not going to actually go through and solve these ourselves in this class, it will be important for you to know how to use the solutions. So you can have equations like this and actually look up the solutions in tables. So we can maybe pick out some here. If you look in E's or look in the textbook, there are some existing solutions to semi-infinite body problems. So for example, the one that we have where we've just got a step change in the surface temperature, that's this problem here. So we're starting at some initial temperature. We change the surface temperature to some different value, and then it propagates the solution right into the domain. The solution to this is actually given by this equation over here. So on the left-hand side, you see this normalized temperature, where we have a temperature minus the initial temperature over the rate over the surface temperature minus the initial. So this is always going to be between 0 and 1. And then we have this error function that's sort of dictating how the temperature varies as a function of x and as a function of time. And this is implemented in E's here, right? So this is the temperature profile, and then this is the heat flux at x equals 0. So you can just use these solutions, right? You don't have to know how you got to the 1 minus error function, but you can actually use it if you know that the conditions are right. In this example down here, there's a heat flux that's applied to the boundary, so it's not like changing the temperature, but it's suddenly applying a heat flux to the boundary. The solution to this looks like this. It's implemented as semi-infinite 2 in E's. What you'll notice is that all of these solutions, or most of these solutions, are for semi-infinite walls. So if you are paying attention, you know that like there's really no such thing as a semi-infinite surface, right? There's, even for something like the Earth, which has a surface that's very, very deep, it's not infinitely deep, right? So the important thing is to note that as long as the thermal wave has not reached the other end of the domain, right? If that's a plane wall, even if it's a very thin wall, as long as it hasn't reached the other side of the domain, it behaves as if it's a semi-infinite problem. Once that wave has reached the other end, then you have to go to different solutions. So these are some of the ones that you'd find in the textbook in table 6.1, and there's some other ones that you can look at. But you should maybe be comfortable knowing how to take these and actually apply them to a problem.